Last time we ended on the cliffhanger of L1 is not even a normed space because, okay, by L1 I mean ordinary L1, because the norm of something being 0 does not mean it's the 0 vector, right? There are some things who are not the 0 vector, also known as not the 0 function, because the functions are fancy vectors, whose norm is 0, right? And we talked about this definition of a null function, so a function whose integral of the absolute value is 0, and some examples are like the indicator functions of the rationals, things like that. And the problem is that ruins our day, because now we have things whose norm is 0, but are not 0. And so technically, capital L1 is not a normed space, because the norm does not satisfy the only thing whose norm is 0 is the 0 vector. And we're going to do a little sneaky sneak and replace capital L1 with script curly L1, and we're going to fix the problem. And fixing the problem involves these things called equivalence classes. And as a little warm-up, I'm hoping you've seen some equivalence classes before. Put your hand up if you've seen an equivalence class before. Okay, fantastic. So this is like a little warm-up on an equivalence class to see if you can cut through all the jargon and understand what it means. It's a pretty, sometimes there's a lot of notation, but it's a nice idea of dividing your space into equivalence classes. So what I did here is I listed the 3 properties that a relationship has to have for it to be called an equivalence class, or an equivalence relation. And then the equivalence classes are the things that are all equivalent to one element. And you write them with this little square. So for example, in my example, it's an equivalence on Z. So I made this new equivalence 2, which is on Z. And so, like the integers, and open square bracket 1, close square bracket means all the things that are equivalent to 1. Those are the equivalence classes. When you have such a situation, you can do nice things with it. But to see if you guys have seen this kind of thing before, I made a little dopey problem. Will you tell me this equivalence class has a name that you've heard before, and I want you to type it in, and then we can go from there. So I'll give you a minute to think about this. Let me know if you need more time to read. If all of this, if you're rusty on all this stuff. Another thing you can do, if you already know the answer, you can check how would you prove these 3 things about equivalent 2 on your homework, which has just been posted as of this morning. You have to prove this equivalence thing for something we're doing with integrals. You'll see what it is in a second, but it's a good check. How do you prove these 3 things for some rule like this? Okay. Okay, and let me bump this up.
Okay, what A related to every element in equivalent to its left.
Every element has to be equivalent to itself.
Yeah, no, just read what.
Oh, it says it's left. Yes.
And also in every element in equivalent to its left.
Every element. Oh, in I guess the set or is equivalent to itself. Sure.
Set is it's kind of it's I'm going to say B.
Yeah, it was definitely something. That's the real goal. I can do that one. Do that one. Yeah. It's kind of random.
A minus B is C.
That's what that was the first that I was though. It's like a negative.
Yeah.
That's what I was thinking. Looking at the. I know when they're actually yeah. But I figured that out though. In this problem, like actually.
Oh god.
Because they're
I thought no, I'm gonna do it today, and then I remembered that.
Okay.
I always forget.
20 seconds left. Put in what you think this set is called to regular people who don't like notation.
That I don't bring my notebooks because I don't have. So every time I go to this notebook because I don't have today, I have to search everything I need because it's written on my notes.
Okay. Let's take a look. What is this thing called? The set of things that are equivalent to the number 1 is called odd numbers. Odd underscore numbers. Odd numbers. This person was off. They said even, it's odd. Okay. The odd integers, the odd numbers, very nice, odd integers. Okay, so this is the odd numbers. That's correct. Odd numbers. Some other people got it even though you weren't graded right.
Well, I'm gonna update it.
So this is the idea. We started with all the infinite integers, and we can divide it into two sets, the even numbers and the odd numbers. How do you do it? You make this equivalence thing. You say two numbers are equivalent if they differ by an even number, and all the numbers that are equivalent to 1 are the odd numbers. And you can check that this satisfies all three of these things. Every number is equivalent to itself, right? Because 0, a minus a would be 0. 0 is divisible by 2. I saw a Twitter post the other day where someone's math teacher told them that 0 is not an even number. And then they had to like appeal to like higher and higher levels of math professors until they agreed that 0 is an even number. Anyway, 0 is an even number. Everything is equivalent to itself. If a is equivalent to b, then b is equivalent to a because a minus b and b minus a. If that one is divisible by 2, the other one is negative of it, it's also divisible by 2. And finally, if you add up two numbers that are divisible by 2, then you'll still get something divisible by 2, which will prove number 3. So you have to do like a little mini proof, but it works. And then you have these equivalence classes. And the nice thing about equivalence classes is as long as it obeys all these things, you can do things with the equivalence classes. So you can work, instead of working with all the possible integers, you can work with the equivalence classes of the integers. And you can do addition and stuff with them. So in our dopey example, you can do the addition of 0 plus 1. This is adding 0 represents the even numbers, and this is odd numbers. And you can add them together, so this is all in this tilde 2 business. What happens if you add the even numbers and the odd numbers? Well, what we're trying to say is an even number plus an odd number is another odd number, so you're going to get the 0 plus 1, which is 1, which is the odd numbers again. So you can take the operation of addition, which was on all the integers, and now it's on these equivalence classes. Sometimes people write the equivalence classes is this set. So we get this new set where we can do stuff. And people write it like this. They do z, and then they do a big divide by the equivalence class. And this means modulo the equivalence relationship. And this is the set of equivalence classes. If you're doing it with this one, it turns out there's only two equivalence classes. There's only even and odd. So this is the even numbers and the odd numbers. And they're equipped with all the regular things. Like you can add them, you can multiply them by scalars. Anything you can do to an integer, you can now do to these things by just upgrading. So for example, if you want to do lambda times 1, where lambda is a number, then you get lambda. Lambda has to be an integer, because if you multiply by a non-integer, you'll get a non-integer. That's not allowed on z, right? What are the things you can do for numbers in z? You can multiply by lambda. Okay. So for example, if you multiply by 2, you're going to get 0, the even numbers. Okay, so this, I hope you've seen something like this before. There should be sort of a recap. But this is like vaguely how it works. We took all infinity things. We took some relationship, and then we created equivalence classes, and that was like a simpler space. And it kind of distills down the things we care about. What do we care about? Well, if we only care about the remainder when you divide by 2, then two things that have an even remainder are the same, and so the only things we care about are even and odd numbers. All right, that was like a little bit of a warm-up. Any questions or comments about this? This is jogging people's memory for how this stuff works. Did you guys take like an algebra class on like rings and stuff? No. Okay. All right.
Yeah. I think proof sets and numbers.
You do it in proof sets and numbers.
Yeah.
No, you don't do it in proof sets. Well, you do this in proof sets and numbers, but not.
I did that when I took it.
Equivalence classes we did.
Yeah.
Equivalence classes and relations, yes.
I see.
Yeah.
Well, okay. A ring is things that are like numbers.
Oh, ring. Yeah.
So a ring is anything you can add the stuff together. You can multiply, and things have inverses.
Right.
And this is the ring called Z2, which is this. You can make a ring called ZP for any P. We use Z mod. Two things are equivalent if they are a multiple of P, and P is a prime number. Then you get the numbers 0, 1, all the way up to p minus 1. And this is a useful ring in cryptography. So this is how they do everything in cryptography. When you send messages, you make them mod p, and then you do a bunch of theorems in p to like laugh at people when they can't factor your prime and like your coding system works or something. Okay. So it's called a ring. I don't know, maybe you did this without calling it a ring.
We didn't really, we saw it like mostly to do partitions.
I see. I see. Okay. Well, anyway, what do you need to know for this course? You need to have heard of this modulo p thing, because this is how we are going to rescue L1, right? L1 has this problem that two functions, they might not be the same function, but their integral is, the integral of something is 0, but it's not 0. So how do we rescue it? We're going to rescue, here's our attempt to rescue it. We're going to define equivalent up to Lebesgue integral. So this is how we are going to rescue L1. We're going to define equivalent, let's call it Lebesgue. I don't know, I'm probably only going to write this one time because it's annoying, but just so you don't mix it up with the other one. What does it mean for two functions to be equivalent? Well, when it was 0, the things that are equivalent to 0 are the null functions, right? The ones whose integrate to 0. So what are two functions equivalent? Well, we'll take the difference of the functions, f minus g, and we'll integrate it, and we want to get 0. So if you have two functions, and you subtract them and take the absolute value, and that integrates to 0, then we say they're equivalent. Okay. And as an example, f is equivalent to 0, the 0 function, if and only if f is a null function. That was the definition of a null function. So the null functions are the ones that are equivalent to 0. So now we have an equivalence relationship, and we're kind of saying we only care about things up to equivalence. Like if the function f is equivalent to 0, then it might as well be 0 for everything we want to do. Like we're not going to distinguish and be like, well, that function isn't 0. No, it's good enough. It's close enough to 0. So what we're going to do is we're going to take L1, right? That's the set of all functions. This is all possible functions that are Lebesgue integrable. Possible integrable functions. And we are going to do the quotient by the equivalence, right? And this means modulo equivalent. Okay, and so what is left are you have equivalence classes of functions. This is the set of all equivalence classes. So an equivalence class looks like square brackets f, and it's the set of functions g such that the integral of f minus g equals 0. And I think a really good example is if you look at the equivalence class of 0, this is the set of null functions, right? So instead of saying 0 is literally the function that's always 0, we're talking about the equivalence class, which is all the functions that are null functions, and we treat that whole group of functions all together as one thing. And that space, this space is called script L1. Okay? And this rescues the problem. Before we had the problem that the only thing whose norm, the problem was that some things their norm was 0, but they weren't the 0 function. But now all the things that were 0, those are the null functions. Those are all one thing that we call like the 0 set, right? The equivalence class of 0. And so this thing is okay. Now the norm makes sense. And so to be crystal clear, we have to move all our operations. So L1 of R is a normed space, right? And you have the operations. If you want to add up two equivalence classes, so somebody tells you, I want to know what is it the plus of this equivalence class plus that equivalence class. Well, you just take the equivalence class of f plus g. That's exactly like the even numbers and the odd numbers, right? If someone says add the even numbers and the odd numbers, then you take some representative from the even numbers, some representative of the odd numbers, add them together, and then take that class. Similarly, if you multiply by a scalar, same deal. So that's lambda f. And if you want to do the norm, this is, I guess, the last thing to do. So you take the equivalence class, you take the norm in L1. What you do is that's just the norm of f in ordinary L1. And this last one, I guess, technically is the only one that you would have to check something. The other two, as long as it's an equivalence relationship, will work. But this one, maybe it's not defined. Like maybe if I take an f and then my cousin from Romania takes a g from the same equivalence class, and we both go to compute the norm, we get two different answers. Like that would be a problem, right? That would mean this thing is not defined. But fortunately, you always get the same answer. So always same answer. Same answer. And let's try spelling answer a little better. Okay, answer. So I guess the norm of f in L1 equals the norm of g in L1 for all fg in some equivalence class. So if you take two different functions from the same equivalence class, they have the same L1 norm. That's like a fun little exercise that you have to check. And all of this stuff proving that it's an equivalence relationship and this kind of thing, I left it for you as a homework problem. It's not too tricky. Okay, so that's how we're going to rescue. Yeah?
Can you just scroll back up really quickly? So
yeah, absolutely.
What you wrote the null functions as?
Yes, 0, so the equivalence class of 0.
So it is equivalent, okay.
So if you're equivalent to 0, then you're a null function.
Yep.
That's like the definition of the null function. Yeah. Right. Okay. So, yeah.
What's the slash in the
The slash. Okay, right. Okay. So this line you would read out loud as modulo, and then you would modulo by the equivalence relation. So that's why I did this analogy over here with the even numbers. So if equivalent means the difference is divisible by 2, and then you do z, this modulo line, so that means look at the equivalence classes mod the equivalence. Then, so for even and odd, there were two of them. There's the equivalence class of 0, there's the equivalence class of 1. It happens those are the only two things. That's because every other number is in one of those two equivalence classes. In our situation, okay, there's still infinitely many equivalence classes, right? So there's the equivalence class, like you could say it's the set of all this thing. Let's make this an equal sign. This thing. So it's the set of all possible equivalence classes. So it's a set of sets, right? So it's the set of all possible equivalence classes of f, right? There's still infinitely many of them. It's just that we've taken all infinitely many functions and we've grouped together all the functions that are whose difference integrates to 0. And we said that's one equivalence class. This is another equivalence class, which is just like taking all the numbers and saying all these even numbers, those are all one equivalence class. All these odd numbers, those are another equivalence class. It just so happens that there's still infinitely many left over. Yeah. Okay. Great question. Any other questions? So it's a very weird idea if you've never seen it before. If you've seen it before a little bit, the more you see it, the less weird it feels. And you're like, yeah, of course. 20 years after you see it, you'll be like, of course. Thanks. When you teach the course on advanced analysis, you'll be like, oh, yes, of course. Okay, so here's the trippy thing. So now it saves it, right? So now L1 really is an actual norm vector space, and everything's fine. Here's the trippy thing. If I say, okay, so now we have some f in the actual space L1, right? And I say, what is the value of it at, let's say x equals 0.5, right? This is like a thing, right? If you have a function, one of the most basic things you want to do is like plug in x equals 0.5. All right. Unfortunately, there's a problem with this, okay? What is the problem? Yeah.
There's a whole class of functions to choose from to evaluate.
Yeah, exactly, right? And okay, well, so that could be a problem, right? This is not just one function, it's a whole class of functions. And that was a thing before, right? But then before it was okay. It was like everything in the class agreed. So if you have to do something to the class and you pick one guy, you better hope that it's going to be the same answer no matter what you get. This is like the cousin in Romanian problem. Okay, but is picking out the value at x equals 0.5, is that the same for every element of the class? And the answer is definitely not. And that's because you can do like f plus the function, which is, let's say 1 at x equals 0.5 and 0 at x not equal to 0.5. This is the classic nullest of null functions, right? The indicator of the set 0.5. This is a null function, and now you have added a null function to f. So this thing is still in the equivalence class of f, right? Their difference is this stupid null function. And so this guy is definitely still in f. Okay, let's do it in black. So this is still an f, but it has a different value, right? Whatever the value of f is, the value of this thing is going to be f plus 1. So I don't know, let's call this function g. So g of 0.5 equals f of 0.5 plus 1, but both still in f, right? And so you can no longer, if you want to work in the real space L1, you can no longer ask for the value at a single point. Excuse me. In fact, you can no longer ask for the value like at the rationals. Like that could all change. If you want to ask for the values at some points, it has to be like a chunky part of the real line that has some non-zero width, sort of. So you can ask for like all the values between 0 and 0.5. That sort of, you can't change all of those without changing the set. So this is like a real issue. Yeah.
So if you pick every number between 0 and 0.5,
yeah.
wouldn't there still be a problem if a function deviates from that interval in some finite points?
Yeah, right. So again, you can mess up all the numbers between 0 and 0.5. You can mess up countably many of them.
Right.
And in fact, you can mess up uncountably many of them as long as you do it in like a smart way. But you can't mess with a whole interval all at once, because then the interval will change and then you'll be out of it. So it's kind of like it's actually a little bit trippy if you think about it, right? It's like what the hell is this thing anyway, right? There's so many functions in there. There's so many null functions that you could add on. You can change the value at like many points, but just not a lot of points. And I think the way your brain should try to resolve this is that sets of measure 0, like countable sets, are just so wimpy compared to like actual chunky sets, like 0 to 1. Like 0 to 1 is so much bigger than the rational numbers that somebody coming along and be like, aha, I messed up your function, all the rationals. You're like, well, you're an idiot. Like, there's so many more. Like, you didn't do a lot. And it really is because the like infinity between all the numbers between 0 and 1 is just way bigger than any countable infinity, right? So yeah, okay, it's kind of like sad, but that's the universe we're in. Okay, yeah.
When you defined the Lebesgue equivalence,
yes,
it was when they're in the integral of the difference is 0.
That's right.
Is that integral on a specific domain? Is it 0 to 1?
No. So okay.
Anywhere?
Yeah. So this is the book does everything Lebesgue measure on R, and everything still makes sense. I think if you want to like imagine L1 of 0, 1, you have all the same arguments apply, and then you like have like one less infinity in your mind to deal with. So I think if that helps you to think about that.
Yeah, it does. In the original definition, it is saying along all the real numbers that interval.
That's true. Yes.
Okay, yeah.
Right. Yeah. Right. Yeah. So L1. I mean, the whole book just does everything with L1 of R, and it's really not a problem because all the integrable functions are made of limits of step functions. So, and step functions are only non-zero on a finite interval. So the way you get to all of R is by doing limits, while you go like further and further out. In fact, you have one homework problem like that as well.
Yeah.
But yeah, so if you understand L1 of 0, 1, going to L1 of R, you should just think about it. Okay, we just make the 0 to 1, we make 1 to 2, we make 2 to 3, and then we like add them together in a smart way. Then we'll have L1 of R. So L1 of R should not scare you more than countable sums of L1 of intervals. And everything in L1 of an interval is already a countable sum, so it's really not any extra work. Yeah. Okay. Yeah. Great question. Okay. So now hopefully you guys appreciate the weirdo quote. I'll read it one more time. Now it will make sense from the book, right? Let's bring this thing back up. Okay. Right. We can only wait. That's not the one.
That's not the one.
This one. Okay. So the whole construction might seem artificial. That's what we just did, this weird modular thing. In practice, we do not often distinguish between script L and L1 and formulate everything in L1. So what this is saying is, okay, actually I just showed you how this stuff works. In practice, what we're going to do is we're going to always work in capital L1. We're not going to worry about this script L1. We know it's there, and we're just going to keep in the back of our mind that when something is norm 0, it's not actually literally 0. It's just a null function, okay? That's really the biggest thing. And you're going to see, as we go on today, we're going to learn about almost everywhere convergence. And we're going to see that being a null function is the same as being 0 almost everywhere. Okay? And so we're just going to keep that in our mind. So we're always going to work in capital L1, not in script L1. So this does not cause any real difficulties as long as you're aware of the problem. That's why I'm telling you now you're aware. Okay. Actually, when dealing with script L1, new difficulties arise. For instance, note that for a function f in L1, it's not actually one function, it's an equivalence class of functions. You cannot specify the value at a point. That is what I just showed you. Okay. All right, so we're gonna move on because now we have like built up all the tools now of the Lebesgue integral, and now we can start to talk about convergence in this space in L1. And we can talk about convergence in norm, and we're also going to see this almost everywhere thing. And we're going to see, this is me putting on my probability hat. Let me write down what this says on the thing. We're going to see that actually you can replace all of this stuff about null functions. We're going to see that f is a null function. A null function. That's going to be the same as f of x equals 0, quote, almost everywhere. Almost everywhere. What does almost everywhere mean? It means that if you picked a random number, then if you did f of u, and you asked for what is the probability that f of u equals 0. So u is some random number between 0 and 1. Now I'm assuming that the function is really on 0, 1. But that's fine. Okay, well, let's say f on 0, 1 to cover myself. Okay. So f of u is some random number between 0 and 1. U is random between 0 and 1. You apply f to it. You get some other number. What's the probability it's equal to 0? Well, it will be 100%. 100%. So the null functions, they are 0 sort of almost everywhere. That's what the almost everywhere means. In the sense that if you ask for the probability that it's not 0, that is a 0% chance. The probability that f of u is not equal to 0 is 0%. It's not literally everywhere, but it's almost everywhere. And in probability, sometimes people, instead of saying almost everywhere, they say almost surely. Almost surely. Right? And almost surely is this idea, it's 100% chance, but that doesn't mean literally everywhere, because there are some sets that are not empty, but have 0% chance. And that's exactly what we're trying to say. Don't worry about those. Okay. By the way, almost everywhere, you'll see it very often as AE, because people are lazy, in particular, your homework. Okay. Question?
Sometimes when we see something called mu almost everywhere, is that the same thing?
This is great. Okay, so this is Lebesgue almost everywhere.
Okay.
Lebesgue almost everywhere. Technically, everything we're doing is Lebesgue. And why is it Lebesgue almost everywhere? It's because its u is the uniform distribution. You can have other measures mu, which would be a fun project for someone to do. Mu, and if you have mu almost everywhere, that is telling you the probability of f of x equals 0 is 100%, where x is drawn according to mu. Okay, something went crazy with my pen here. Okay, let's try this. Everywhere. And okay, for a lot of random variables, like a Gaussian or something, it's exactly the same as Lebesgue almost everywhere. But if you have a random variable that has different probability structure than just having different chances everywhere, then it can get weird. So like if mu is like a Cantor set or something, then it's like some other thing. But yeah, same idea. Great question.
Mu is just like a measure.
Mu means any measure that I'm thinking of.
Okay.
Yeah. And in this class, we're going to think about the Lebesgue one only.
Okay.
Yeah. Okay. Other questions? Okay, so let's start moving. We're gonna move into this. We're gonna do the two sections we're gonna work on today are convergence in norm and convergence almost everywhere. So section 2.6 is convergence in norm. In norm, which just to warn you, in the textbook they do IN, which to me is like too lazy. Like, come on, it's like 6 letters. And we're gonna do 2.7, which is convergence AE. And that one I'm on board with, because almost everywhere is a lot more letters. Okay, so we're gonna start with these things, and we're gonna see that all this stuff about null functions, it really comes out in this like almost everywhere and in norm thing. Okay, so the first thing we're gonna show, theorem 2.6.5, if Fn converges to F in norm, So again, this is like the usual thing we did in chapter 1, right? That means the norm of fn minus f goes to 0, or the integral of fn minus f goes to 0. Then what? Then the integrals are equal. Then the integral of fn converges to the integral of f, which is a nice property. So if they're converging, their integrals as numbers also converge. And the proof is very simple. It's like a one-liner, just by triangle inequality, which we've done many versions of so far. If you look at the difference of fn minus f, that is less than or equal to the integral of fn minus f. This is exactly one of the inequalities we proved along our journey to defining all this stuff about the Lebesgue integral. So sort of all our hard work, all these theorems we proved that were like really annoying. We had to like worry about, oh, f is some sum of step functions and blah, blah, blah. It's just like now we use them and they do exactly what we need. Right, and this integral goes to 0. That's exactly what it means. So you're less than something going to 0, then you also go to 0. Yeah.
Is fn any function or a step function?
No, here fn is any integrable function. Yeah. Right. Yeah. So you should think of the step functions were like the Lego that built everything, and now we have everything built, and we can like play with like a full Lego house. So we don't have to worry about the blocks.
Okay.
Yeah. Okay. All right. Okay. Here's another good one. Next one in the textbook. Theorem 2.6.6, which says if f is sim equal to f1 plus f2 plus dot dot dot, and they don't have to be step functions. So now they can be any integrable functions, right? And that's because, again, last class we proved that if you make a sequence of integrable functions and add them up like this, that's what I called super integrable, but that was just the integrable functions again. So now you can, this is one way you can build a new integrable function, is by adding together integrable functions that you want according to bullet points A and B of that. And so last time we had the sim equal, we had part A and part B, and now I'm telling you that it implies that then the sum of n equals 1 to infinity of fn converges to f in norm, right? So kind of this like special equal sign that we've been like floating around for so long. We had to use it to define the norm, but now that we've defined the norm, it really means it implies convergence in norm. So great. And the proof, again, is very simple, because given any epsilon greater than 0, by definition of this funny sim equals, find n naught, so that the sum of the integrals of fn are less than epsilon, right? So I think one of the two conditions is that this infinite sum is summable. So make it less than epsilon, and that will be for n bigger than n naught. And then you have, again by all the triangle inequalities we proved, that f minus the sum of the first n naught, well, that will be less than the sum of n greater than n naught of absolute value of fn, which is less than epsilon. So the norm of this f minus the sum is becoming less than epsilon, and we can do that for any epsilon greater than 0. Therefore, they can converge down to 0 in norm. I believe the theorem we invoked here is theorem 2.3.1, way back when, which was several classes ago now. Okay, so that's convergence in norm, and like really, we're just checking like the things that we want convergence in norm to do. We already know about convergence in norm from chapter 1, and now we're just like seeing it in this Lebesgue space, and it does all the things that we think it should do. Okay. Questions or comments? Yeah.
This might be obvious. How did we get the inequality? Is it just in the theorem?
Yeah, the theorem says. I'll tell you what the theorem says. The theorem. Let me remind you what the theorem says. The theorem says, I'm going to use g's, so we don't get mixed up. It says if g is g1 plus g2 plus dot dot dot, then the integral of g is less than the integral of the sum of the gn's, or something like that. I think that, and this was one we proved last class. And here what I did is I just moved the first n naught terms over, and then it worked. Yeah. So okay. No, that's a good clarifying question. Okay. Yeah. Any other? All right. And so now we're going to get to a little more of an exciting thing, which is 2.7, which is convergence almost everywhere. And this starts to get a little more slippery. So convergence almost everywhere is kind of like pointwise convergence. Pointwise convergence is convergence everywhere, and this is convergence almost everywhere. And so we're going to like dig into what this actually means, and you're going to see how the norm plays with these almost everywhere things. Okay. We're going to start with this definition that I already gave you, but in the book it comes later on. It's the definition of a null set. 2.7.1, a null set. A null set, and that means x is a null set. That means the integral of the indicator function of x equals 0. So it's, in the book they say its characteristic function is a null function. So it's the sets where when you look at the function that's 1 on the set and 0 otherwise, that is integrates to 0. Yeah.
So just to like clarify,
Mhm.
a null set is a set with a measure 0.
Sorry, what?
So if I have a measure, the set is a null set with respect to the measure if the measure of the set is
Yes,
0.
right. These are sometimes called measure 0 set. Null set means x is measure 0. The measure of a set, I can tell you what the measure of a set is. The measure of some set x is the integral of x. So if you want to measure how big a set is, you make the function that is 1 on the set and you integrate it. So for example, the measure of the interval 0 to a half, you take a function that is 1 between 0 and a half and 0 everywhere else, you integrate that up, it's going to be a half. Actually, this is a step function in this case, so it's great. And so the measure will be half.
Just asking because it's the definition we see
Yeah.
in other places.
Right. So yeah, this is, I think I mentioned this once, but let me mention it again now. Because now that we're kind of through the hard part of the Lebesgue integral, a lot of courses start with measures. So they say like, how do we define the measure? What's the measure of an interval? Blah, blah, blah. And then they build up, using the measure, they build the Lebesgue integral. This book goes the other way. So they start with the Lebesgue integral, and they have this tricky sim equals infinite sum thing, and that lets you skip over a bunch of stupid technicalities with the measures. And like you can take a whole course just on measures. So when I was an undergrad, we took 2 courses. We took one whole course on measure, it was like a third-year course, and then we had another course in 4th year on analysis. You guys only get 1. So that's why we kind of skipped some of the stuff. But it is a great project if someone wants to do something like that. And for example, you can make a non-measurable set that's really fun, or you can talk about these weirdo measures like the Cantor measure that is like super weird. Okay, wait, I can't resist. We have to take a second. Where's my mouse? Okay, I'm gonna search for the right thing. Devil's staircase. What is the devil's staircase? All right. So if you search on Google for the devil's staircase, it shows you some stupid thing in Arizona. That's not what you want. You want to click on Wikipedia, and you want to find the math one.
The Cantor function.
Look, other uses, a singular function in mathematics, the Cantor function. This is the coolest one, okay? You click on this one. Okay, this is some weirdo function. What does this function do? This is a function whose derivative, wherever its derivative exists, is 0 everywhere. Its derivative is always 0. And yet the function is increasing. The function, and it's continuous. It goes from 0 to 1. It's increasing. And its derivative, wherever it exists. By the way, its derivative exists almost everywhere. Now you know what almost everywhere means. So the only places where its derivative does not exist is a null set. The probability that its derivative is 0. You pick a random point. The probability that it's differentiable is 100%, and its derivative is 0 everywhere. And yet this function goes from 0 to 1 somehow. The answer is it has this tricky set called the Cantor set, and it's increasing only on the Cantor set. In fact, this is the cumulative distribution function of some kind of random Cantor set. So you pick a random point in the Cantor set, that's the cumulative distribution function. So this is a great project if someone wants to do this. And in fact, in the textbook, they have as an exercise to prove some stuff about the Cantor set. So that's a great place to start. You can do those exercises and like look up how to do them, and then that'll be a good place. So this is a really fun function. Yeah, this is everyone's coolest function. Look, here's how they make it. How do you make a function? It's a limit of other functions, right? It's a good thing we're doing the Lebesgue integral or nothing would make sense. But you start off with a function that's kind of boring, and then you add more and more pieces to it and in the limit, it converges to this weirdo function. What else can I say about it? Properties? I don't know. Lack of absolute continuity. More definitions. Oh, it has a fractal volume. Okay, great. Amazing. Okay, I'll stop there. Nobody asked me any questions about the Cantor function. I didn't prepare. Okay. All right. Other questions or comments? Yeah.
Not about Cantor function.
Yeah. No, you can actually ask me. Okay.
You've said a few times that the integrable functions are the limits of a sequence of functions.
Yeah.
Are those functions that in this sequence, are those the first n terms of this sum?
Yeah, what I mean literally, like if you go back to the definition was f is this kind of thing, f1 plus f2 plus ... So I mean these functions, and it's a limit in a very particular sense. It has to satisfy a and b, where a and b were like the definition of this thing. And the point is that these f1, f2s in the definition, they were step functions. So it really is like we have the simplest possible things, the step functions, and we built all the integrable functions by doing this specific type of limit of those things. Now that we've defined everything, you're going to see that it really is just saying that it converges in norm and it converges almost everywhere. We're going to prove both of those things soon. But it's really this specific type of limit, and like that constructs all the integrable functions out of limits of these like baby functions. Yeah. Okay, yeah.
You're talking about the indicator function, right, in the definition?
In this definition, I'm talking about the indicator function. Yes, that's what one means. Yeah. Oh, I'll warn you guys, some books, they do a chi. So chi x, because that's not confusing. But yeah, just watch out. And some people call this the characteristic function. You also have to watch out because characteristic function also means some other thing. So like, I think the moral of the story is mathematicians are bad at naming things, so watch out. Just be ready. Okay. All right. Okay, where are we? Any other questions? Okay, so we have these null sets. What does convergence almost everywhere means? It means convergence except for a null set. That's what the almost in almost everywhere means. Yeah, the definition, f equals g almost everywhere, AE, means if you look at the set of x, where f of x is not equal to g of x, the set where they're not equal, that is a null set. Okay, and again, putting on my probability hat, you would say f equals g almost everywhere. It means the probability that f of u is not equal to g of u equals 0. Right? So if you pick a random point and you ask, are they equal? There's a 100% chance the answer is yes, they're equal. There are some points where they're not equal, but those points have a 0% chance of getting chosen. All right, that's almost everywhere. Those are null sets. Here is a cool fact about null sets that has a very interesting proof in the book, which is theorem 2.7.2. Any subset of a null set is still a null set. It's a very reasonable theorem. Any subset of a null set is still a null set. Okay? And actually, the only hard part about this is if you take a subset of a null set, maybe it's a set who's not integrable at all, right? So the real meat of this theorem is question, let's say A is subset of B, and the integral of the indicator function of B equals 0, so B is a null set. Is A even integrable? Is the integral of A, does that exist? Because if it exists, then that function is less than that function, and then it's fine, but it might not even exist. And we saw last time there are some non-integrable functions. You can make them with the axiom of choice by some crazy method, so you got to be careful. And so the textbook has a really funny proof, which goes like this. Okay, I guess I have to, let me translate it. Okay, in the textbook it's written with functions. So in the textbook they do it like this. They do there's some 2.6.3, and they say if g is less than f, and the integral of f equals 0, then g is integrable, and the integral of g is 0. Okay, let's write this one out. Is integrable, and the integral of g equals 0 in absolute value. Okay, and I think it actually needs to be an absolute value. Let's do it. If g is less than f. There we go. Okay. If you know this one, then that one follows by putting f is the indicator function of b, and g is the indicator function of a. But let's do this one. This has a really funny proof. Here's the claim that looks so bizarre, is that g is sim-equal to the following infinite series: f plus f plus f plus f plus dot dot dot. You add up f's forever. And this seems like totally crazy, right? How can you, if you add up something forever, this is like what you learn in infinite numbers 101. If you add up the same number over and over again, it is not going to converge. You can't just do 1 plus 1 plus 1 plus 1 plus 1 and hope it converges. The numbers have to get smaller or something as you go down, or else it's not going to converge. So what is going on here? Well, actually, the integral of f is 0. So f is mostly all zeros. There is one special number you can add up over and over again, and that's 0. And f is mostly 0. So this thing actually will work out because f is mostly 0. So it looks crazy, but it works because f is mostly 0. We have to check a and b, right? A and b, properties a and b, which are the heart of this construction with the sim equals. And property a says the sum of the integral of f, so it's f1 plus f2 plus f3. Here we have f repeated. So the sum from n equals 1 to infinity converges. So the sum of the integrals converges. Well, the integral is 0 here. So it does converge, right? 0 plus 0 plus 0. You add up the integral, it converges. Yes, it's all zeros. It's all zeros. Okay, property B says that g of x has to be equal to the sum of f of x whenever sum converges absolutely. Okay, but when can the sum converge absolutely? You're adding up infinitely many copies of a number. It converges absolutely exactly when f of x equals 0. So we only have to check that this thing equals that thing when the absolute value of f of x equals 0. And when the absolute value of f of x equals 0, it is true that g of x equals this stuff. Why is it true? Well, g is less than f. What numbers are less than 0? The only possible thing is that g was 0. So, and this is true since g of x equals 0 whenever absolute value of f of x equals 0. So this is like a really funny proof that if you have a null function, you can add up the null function together infinitely many times, and it will be sim equal to some other functions. Right? And in fact, what's happening is that these two functions, they just both happen to be 0 on the same set, and there's some nasty, dumb stuff on not the set where there's 0, but that nasty, dumb stuff is a null set. The set where f is not 0 is some tiny, tiny set. It's almost everywhere 0. Okay. And this proves that the subset of a null set is still integrable. The integral is 0 because the integral of g, by the definition, is the sum from n equals 1 to infinity of the integrals of fn, which is 0. You add up 0 infinitely many times, still 0. Okay. So that's a nice little proof. Okay. Okay. And there's another proof that uses the same technique called theorem 2.7.4, which says that f equals g almost everywhere if and only if the integral of f minus g equals 0. So two functions are equal almost everywhere if and only if their difference is 0. This is a bit like saying the things that are in those equivalence classes that we started the class with. Those are all functions that are equal almost everywhere. just kind of the intuition I was trying to give. Anyway, so those equivalence classes, you can mess up a small number of points, but you can't mess up more than a null set number of points. Okay, and here's the proof. The proof is exactly this dopey trick. The proof. So here I'm going to do two proofs. Let's suppose f equals g almost everywhere. If f equals g almost everywhere, then what I'm going to do is let B be the set where they are not equal. Okay. And that is a null set. Because if they are equal almost everywhere, it means that that's a null set. And then I'm going to claim that the indicator function of the set B is sim equal absolute value of f minus g plus absolute value of f minus g plus absolute value of f minus g forever plus dot dot dot. Again, this is one of those silly things. How could it be that this holds? Oh, I did an oopsie. It's the other way around. Okay, hold on. That's the next part. That's coming up.
Okay.
It's this one. F minus g is sim equal the indicator of b plus the indicator of b plus the indicator of b forever. Okay. How could this be true? Again, it's one of those things. You're adding up infinitely many copies of the same number over and over again. So, of course, this doesn't make any sense except for when you're not in the set B. When you're not in the set B, B stands for bad set, by the way. So when you're not in the bad set, then f equals g. And when f equals g, the left-hand side is 0, and then you're adding up 0, 0, 0, 0. It all makes sense. It's exactly like the proof we just did. So, check conditions. Check conditions. The sum of the integral of the indicator of b, that infinite sum is 0 since it's a null set. That's A. So that is fine. And B, f minus g of x equals 0 for x not in B by definition of B, which is the only place where the right-hand side converges. So in other words, we only have to check that the two things are equal when the right-hand side converges, and it only converges off of the bad set. On the bad set, this is 0. When you get zeros, it's all fine. So it's the same trick as before. Okay, and so if this thing is that sum, then the integral is that sum. The integral of f minus g is the sum of the integrals 1b forever, which is 0. Okay, so that's if they're equal almost everywhere, then they are, the norm is 0, the integral, the norm of f minus g is 0, and the reverse is the same thing using the other proof. Let me make these like more high levels. We don't get these mixed up with the other ones. So I'm proving both ways of this proof, like that, and all you do is the opposite. Now, in this case, we're going to prove the indicator of B is less than f minus g plus f minus g forever, like I originally wrote down by accident. And in this case, if the integral of f minus g is 0, then that will show that this stuff converges. Where could it possibly not converge? The only place it converges is when f minus g is exactly 0. That's exactly off the set B, and so it all works. Show, I want to say by similar argument to save us a little bit of writing. Okay. So there you go. I think this is a really good intuition. This almost everywhere business. The norm is 0 if and only if they're equal almost everywhere. Okay. Okay, here's one more. Actually, let me stop if there's any questions. Here's one more property. I'll leave this one as an exercise. It's very similar to all these other ones, which is, or you can go read it from the book, theorem 2.7.5. If Fn goes to F in norm, and Fn goes to G in norm, right? So if L1 was like truly a normed space and like really obeyed this thing with like the norm is 0 if it's a 0 function, then you can only have one type of limit, right, in norm. But because L1 is not a normed space, like it could be that F and G are just two completely different functions. That can happen. But the thing is, they are two completely different functions, but they are equal almost everywhere. Then F equals G almost everywhere. Okay, and the proof again is not too hard. You can just do some triangle equality and like use the things before it's like a one line. But let's skip it because we're about to come to a fun probability example. Questions? Okay, so we have equal almost everywhere. We have this norm stuff. I told you what equal almost everywhere means. Let me tell you now what convergence almost everywhere means. Definition 2.7.6, convergence almost everywhere. And what does it mean? Fn goes to F, converges to F almost everywhere means the set of X where Fn of X converges to F of X. I guess the set where it doesn't converge. Let's write in big letters, not this is a null set. And in probability language, you would say the probability that Fn of U equals Fn, let's say the limit, is 100%. 1. So you have some sequence of functions, and the probability that it's converging to the F is 100%. This should just say F of U. Okay. I realized somehow we got zoomed out. Let's go back. So there's a 100% chance that Fn converges to F. It's just there's like maybe some couple bad points where it doesn't. Yeah.
Sorry, I don't really understand what you mean by the not.
The not. I mean the limit of Fn is not F of X.
Okay.
Let me write it with a not equal. We have
Okay.
we have a symbol for this. Yes, the limit as n goes to infinity of Fn of U is not equal to F of U. Yeah. I guess if the limit doesn't exist, that counts as not equal. Just that's the only thing you got to be careful of. Okay. Yeah, that is more clear. Okay, that's convergence almost everywhere. So now we have two types of convergence. We have convergence almost everywhere. We have convergence in norm. And we've got a couple of little toolbox theorems that have said things like, look, like this norm and almost everywhere are kind of similar, right? Like something converging in norm and something being equal almost everywhere is like pretty much the same thing. So you might think convergence almost everywhere is kind of the same as convergence in norm. But unfortunately, you are wrong. Okay, and I'm going to give you an example. So this is an example where Fn goes to F almost everywhere, but Fn does not go to F in norm. So here's the example. And okay, you could do this the textbook way, draw the picture, here are the functions, and then it's a fact, like we're done. But I'm going to tell you the fun probability story that goes with this, okay? Because it's not just some functions, it really is about what can you do with random variables? When do random variables converge, and what do they mean? And again, almost everywhere is kind of like converging with a 100% probability, and converging in norm means in expected value do the expected values converge. And to do this, I'm going to set up a probability of having an infinite sequence of coin flips. So this is the only little setup we got to do. Setup. I'm going to make an infinite sequence of coin flips. So an infinite sequence, like heads, tails, heads, dot, 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 and it goes on forever. And I'm going to do this for every possible x in 0, 1. So far up until now, all the little probability stories have been happening on the interval 0, 1, and this story is just like that story. It's something that happens on 0, 1, and I'm going to tell you how you make an infinite sequence of coin flips from a point x in 0, 1. Here's how you do it. Write how? Write x in binary. Okay? So you give me a point x in binary, let's say you give me the point 1/3, and I think then x equals 0.110110. It's some sequence in binary, right? And what I'm going to do is, if the first one is a 1, the first sequence is a heads. If the second one is a 1, the second one is a heads. And just match up 1 with heads and 2 with tails. Match. 1 means heads, and 0 means tails. And it turns out that this works perfectly well. All of the coin flips will be equally likely to be heads or tails. If you pick a random number in 0, 1, all of the binary digits are equally likely to be 0 and 1. Not very surprising. Okay, so this is how you can assign to a sequence of heads and tails. It's the same thing as a point in 0, 1. And now here are my functions fn. I guess before I do the functions, any questions about the setup? Okay, so here's the function fn. Fn is going to be the function, so x is the input, like x is the infinite sequence, and fn is we are going to gamble on the sequence, and fn is how much money we're going to get after we gamble. Yeah.
Is x like a infinite, like?
So x is a number in 0 and 1, but I want you to interpret x as an infinite list of heads and tails, because I'm going to define it in terms of heads and tails, even though it's a function of x. So I'm thinking of x both as a number in 0 and 1 and as an infinite list, and I'm trying to tell you that those are the same thing if you just do the infinite binary decomposition. Yeah?
You said the binary decomposition successfully encapsulates the 1/2 probability.
That's right. Yeah.
I'm confused by why that. I mean, I
Yeah,
understand intuitively.
Yes, okay, let me tell you what. It's great. Okay, let's do the first coin flip. Let's look at the set of binary sequences that have a 0 in the first one, and the set of things that have a 1 in the first one. And you'll see that on the real number line, so 0, 1 is the real number line. If you look at the set of x that start with a 0, it's everything over here. This is start with 0. Start with 0. And if you look at the things that start with 1, it's everything over here. Start with 1. So the first coin flip is equally likely to be heads and tails because they're a half a half. If you look at the first 2 coin flips, you'll get a division into 4, and it'll be 0, 0, there'll be 0, 1, and then there'll be like 1, 0, and 1, 1, and it'll be divided up into 4. And if for any number of coin flips you look at, you divide it into 2 to the end. Yeah, no, it's a very nice property, and it's quite nice. I'll tell you, because I told you something about the Cantor set, and I can't resist. The Cantor set has something to do, instead of coins that are heads or tails, you look at 3-sided things that are heads, tails, or sideways. Oh, actually, that's perfect. Yeah, it's heads, tails, or sideways. And then you do something to it to make it the Cantor set. So the Cantor set, you write out things as not as binary, but in ternary, 0.0122101, and then you do something. Okay, I won't spoil what the something is. Okay. Okay, great question. Yeah, anybody else? Okay, so what is fn of x? It's going to be, we're going to gamble. This is our gamble. Our gamble payoffs. Ha ha ha. A gamble. I was grading, maybe I shouldn't say this. I was grading somebody's assignment today in my other programming class, and there was a gambler. And they made a typo in their code, and they called it a gamblette, which I think is adorable. That's like a baby gambler, right? Okay. So our gamblers pay off.
Got out of the womb into baby.
Yeah, right?
That guy was ready.
Okay, so our gamblers pay off. And here's what it's going to be. Our gambler is going to bet, it's Fn, we're going to bet on n heads coming up in a row. Okay, we're feeling lucky, we're like 10 heads in a row, let's go. Okay, so how much money do we get? And it's a fair at a fair casino. A fair casino. I'll tell you, so if we lose, then we lose $1. We're only going to bet $1. We're going to bet $1. So if we lose, if it doesn't come up first n heads in a row, then we're going to lose $1. -1. And this is if not heads at the beginning. So we don't care, even though it's an infinite sequence, we only care about what happens in the first n. Everything that happens after the first n, we just don't care about. Like, we only get to see the first n heads. And if they're all heads, then we're going to win. And if we don't, we're going to lose. And we're going to lose $1 if we don't. If it is heads, then we're going to have a big payday here. Because getting n heads in a row is quite unlucky. or you have to be quite lucky to get n heads in a row. So the casino is going to give us a big payout. To make it a fair casino, this is a fair casino, they offer even odds bets. Does anyone know how much money the casino would pay you if it's a fair casino and you've got to get heads in a row n times?
How big is n?
N is n. You can handle letters. Yeah.
Is it 2 to the n?
It's 2 to the n. Yes, 2 to the n. And actually, so 2 to the n is the probability of it. 1 over 2 to the n is the probability of it happening. So the casino has to pay you out 2 to the n to make it fair. There is one other small thing. It's 2 to the n minus 1, because you have to pay like an entry fee of $1. You always lose your entry fee, and then you get 2 to the n if you win. You can also think about this. If you go to a casino and you say, I want to bet on heads to come up 10 times in a row, or if you go to the roulette table, because they don't actually have heads and tails, they have roulette. And you say, I want to bet, I get 10 blacks in a row. The casino will say, look, man, you can bet on red or black, and then you can bet again, but you can't just bet on the next 10. You have to bet on the next one. But fortunately, what you do is you just bet on black, and then you double your bet every time, okay? So you bet black is going to come up. If it wins, you double. If you win again, you double. If you win again, you double. And how many times did you double? N times. So that's why it's 2 to the n. You doubled your bet n times. If you win, then you walk away and you win. If at any point you lose, then you lose your whole bet and you leave in your set. Okay, so there's a very nice function, fn. And actually, I will draw a picture for you of fn of x now. Fn of x, you can think about it as a function on 0, 1, right? X is in 0, 1. It's a very simple function. It looks like this. It's 2 to the n minus 1 on the first interval of length 1 over 2 to the n. And it's 0, or it's negative 1 everywhere else. It's negative 1, negative 1. So it's actually the function which is negative 1 if x is bigger than 1 over 2 to the n, and it's 2 to the n minus 1 if x is between 0 and 1 over 2 to the n. And you can see that because in our binary decomposition, what numbers start with heads, 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 heads? It's only the numbers that are less than 1 over 2 to the n. I think I might have flipped heads and tails. Maybe it has to be tails, 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 tails.
I think it has to, because that's a sequence.
Probably. Okay, look, very simple fix.
You can just also put them in.
I'm doing it this way. Wait, no, okay, I had it right. Okay, wait, look, see, I said it technically correct. Okay, so I guess we're betting on heads, 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 heads is the sequence 0, 0, 0, 0, 0, not the sequence 1, 1, 1. Okay, good. That is fine. This is what I wanted.
Does the spike have to be around 0, or could it
Well,
be like around 1?
It could be around 1. Yeah, if you flip heads and tails, it'll be on the other side. But then it's annoying to write down, and you have to do a 1 minus. I don't have room for that. I hit the margin. Okay. So that's what the function fn looks like. This is actually a relative of the sliding spike functions we've seen a few times in the course so far, right? You have a very narrow spike, and the spike is getting bigger and bigger as the width gets smaller and smaller. I'll tell you what the expected value of fn of u, that means flip a fair sequence of points, u is an honest fair sequence of points, expected value of fn of u is the expected value of our bet. And in integral language, this is the integral of fn of x dx. Or as this textbook would say, it's just the integral of fn. And does anyone know what the expected value would be for the integral? I'll let you think for a second. You go to the casino, you make a bunch of fair bets. What is your expected value at the end of the day? 0. Yeah, it's 0. It's 0. And in fact, if you make fair bets at a casino, how could your expected value be anything other than 0? Every single bet you made was 0. I made n bets, put them together, still 0. So it's not surprising. If you make a finite number of bets at a casino that is fair, your expected value will be 0. And you can also check, right? This height of the spike exactly cancels out the negative that is quite wide. On the other hand, let's look at the limit as n goes to infinity of fn of x. And I would say as n is getting bigger and bigger, what is happening? So for some fixed sequence of heads, tails, what is the limit of fn? What is happening? And I claim this is minus 1 except for 1 point. There's only 1 point where it's not minus 1, except for one single value of x. Right? And this is saying, as you bet on more and more heads to come up, eventually you will lose. You will not be heads forever, right? it will be -1 unless there's one exception, which is what if it is heads forever? You could get heads forever. So if x equals heads, 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 heads forever, there is exactly one point, which is heads, heads, heads forever. That's the point x equals 0. So this limit is equal to -1, except for at 0. And so if you ask for what is the probability that the limit as n goes to infinity of fn of u equals -1, it's a 100% chance. There's a 100% chance this betting strategy will leave you with a profit of -1. So as you bet on more and more heads to come up, you're going to have a profit of -1 with a 100% chance, even though your profit on average is 0. All right. So this is an example. The functions fn, they go to -1 almost everywhere, but the integral of fn does not go, they don't go to -1. Let's say fn does not go to -1 in norm. And you can see that because the integral of fn equals 0 always. Okay. So this is kind of like a lottery, right? Like the lottery becomes so unlikely and the payoffs become so large that you just always lose you pay for the lottery ticket, you pay $1, you just get nothing. So far, not exciting. I'm going to do one simple thing and I'm going to blow your mind. We're going to flip it with a negative sign. Let's make the function gn, which is minus fn. And this is a function which is you gain $1 unless it's heads, heads, heads. Unless heads, heads, heads. And when heads, heads, heads comes up, then you lose 2 to the n dollars. Okay? If heads, heads, heads. This strategy, before it was a very simple betting strategy. You just double your bet all the time. You look like you're just being crazy. This one, very civilized betting strategy. This is called the martingale betting strategy. Martingale. Why is it called the martingale betting strategy? There's a fun story. There's a city in France called Martin. Martin, if you're anglicized like I am. Okay. And people from Martin would come to the casino in Paris and do this stupid betting strategy, and they thought they were invincible. Okay. What is the betting strategy? You bet on black, and if you lose, you're like, oh, I'm down $1. Now I'm going to bet $2. And then if you lose, now you bet $4. And if you lose again, now you bet $8. You see, you keep doubling your bet so that when you eventually win, it cancels out all your previous losses and you end up with plus $1. And you will get a plus $1 very high probability chance, right? Unless it comes up heads, 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 heads. What are the odds of that? You get plus 1. If it does come up heads, 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 then you lose a lot of money. And here's the beautiful thing about this betting strategy. It has a 100% chance, if you bet for long enough, of gaining you $1, right? The limit, as n goes to infinity, of gn of a u, it's equal to plus 1 with probability 100%. Okay, 100%. So this is a betting strategy that gains you $1 with 100% strategy. That's a lot more exciting than losing $1 with 100% strategy. That's why I had to bring it up. Okay? So here's a betting strategy. You can gain $1 with a 100% chance. The only problem is the expected value is 0. It's still 0. You cannot escape. And there's a whole theory of martingales, which are these expected value 0 processes and like when you can take limits of them and things. So there's a whole area of probability. Again, this could make for a nice project. There's a very nice book called Probability with Martingales. You could do something from that book. Okay, the thing that I had to show you was a function. So gn converges to plus 1 almost everywhere, but gn does not converge to plus 1 in norm because the integral of gn is always 0. Okay. So there you go. Almost everywhere, and in norm, they're not exactly the same thing. You can converge in almost everywhere, but not in norm. Questions or comments about that one? Let me leave you with a question. Now it's your turn to do a question. What about the opposite? So you've seen an example where you converge almost everywhere, but you don't converge in norm. Can you converge the other way? Is it possible that you converge in norm but not almost everywhere? Is it possible? Is it possible to do the reverse? Yes, it's possible, or no, it's not possible. And again, this is one just based on vibes. What do you think? Can you try to think of an example where it's converging in norm, but it is not converging almost everywhere? That's what you're gonna do. Can you think of such an example? I'll give you, I guess, like 2 minutes to brainstorm an example before I tell you.
The trick here is that we need this disagree to be not needed to have measured greater than 0. What's the definition in norm again? Oh. So convergence in norm means
The integral goes to 0.
the integral was
The integral of the absolute value goes to 0. Yeah.
So we needed a non-zero. The function is going everywhere, but it's 0 at a set non-negative 0. So negative is still going to return 0. Oh, I think I got it. Yeah, I think it is. If I have actually, I'm thinking if we have a function that is like 1, but then someone can disagree, the measure isn't 0, but the function is 0 there. You go back to the super code 0. No, wait, never mind. No, it's not.
Okay, so there's like 10 seconds left. Put in your whatever your vibes are telling you, and we'll see.
I'm going to just remember. I switched the answers by the way. Just that's really, you know, I think I'm going to be the single wrong in this class.
All right, let's see what you guys said. 8 out of 11 people said no, it's not possible. The answer in analysis class, it's always possible. There's always some nasty one.
I should have trusted your vibe, Robbie.
And I will even tell you what the sequence is that does it, and we're gonna go over it next class.
Next class?
Yeah, because we have 2 minutes left.
Oh,
Here's the function. Here's the function that does it. You can, for every sequence. So for every sequence of heads and tails, every finite sequence, let's say, finite sequence of heads, tails, can invent this function. It's the function f heads, tails, whatever. You put in your favorite sequence, right? So your sequence goes here. Okay? You tell me that sequence. And I'm going to make the function, which is 1 if x starts with your sequence, and it's 0 otherwise. And as an example, the function we had before, fn, what I called fn before, was something like the sequence f of heads, n times in a row, multiplied by 2 to the n. You got to pay out, in this function, you only got to pay out of size 1. Before, you got to pay out of size 2 to the n minus 1. So, old example was. So you can bet on, basically, you go to the casino and you bet on any particular, you pick your favorite sequence and you're betting that it comes up, but you only get $1 if it comes up. You get $0 if it doesn't come up, which is actually rather generous of the casino because you're not paying anything, right? There's no negatives. This is a function. If you enumerate these, right? So there's 2 for every n, for sequences of length n, there's 2 to the n such guys. If you enumerate all the guys, so you let gn be an enumeration of f of all sequences. So line up all the sequences and count them up. The first sequence, the second sequence, the third sequence. The first 2 sequences are probably heads and tails. Then it's heads, tails, heads, tails, and so on. Do the line 3 ones. This sequence, gn, it will go to 0 in norm. gn goes to 0 in norm, which is not hard to see. The integral of this thing will go to 0. But gn of x, the limit does not exist. N goes to infinity, does not exist for all x. So for every sequence, this limit does not exist. It goes 1, 0 infinitely often. It will sometimes be 1 and sometimes be 0, no matter what point you're at. And we're going to see exactly why next class. Question here.
If we're mapping the sequences to the interval 0, 1,
Yeah.
and it has a similar cardinality, wouldn't that immediately exclude the possibility of an enumeration of the sequences by virtue of their boundary infinite?
Yeah, that's a great question, but I'm only looking at finite sequences.
Oh, right.
So I'm not. This is a great point. I don't want. You can't do f of an infinite sequence. It's f of a finite sequence, and I want you to enumerate all finite sequences.
Right.
Okay, yeah, that's great. I'll add the word finite. Be an enumeration of all finite sequences. There you go. That's great. Okay, we'll see this one next class. Have a great weekend. The homework is posted. Make sure you go take a look, and don't forget to write up a nice solution for homework 1 to get the boost. Okay.
There really isn't working today.